Hello, friends. So today we are going to have a anchored sheet pile, and we are going to solve it by fixed earth support method. So this is the anchored sheet pile, and this is the backfill, which is sandy in nature. So it is going to penetrate the sandy soil. So this is the dredge line DL, and the anchor rod is provided at a height h1, and the water table is at the height h2, as shown in the diagram here. The force in the anchor rod is shown as F, and you can see the pressure distribution diagram. The pressure is going distribution diagram. It is going to be active earth pressure, that is K into gamma into Z up to the water table, and below the water table it is going to be K gamma prime into Z. So the pressure distribution active, and then it is going to be a active and passive in this zone. So it is going to turn like this, and finally this is the pressure distribution diagram. If you see the deflected shape of the anchored sheet pipe in the fixed earth support method, if you take it very deep, the deflected pattern is going to be like this, as shown in the dotted line. So the deflected shape of the sheet pipe is shown by the dotted line, and point I is the point of inflection, and therefore the pressure distribution diagram has been shown over here. And if you want to draw the moment diagram, bending moment diagram, then what you can do it, you can consider the equivalent beam concept. So here, from G to A, the top point is A, anchor rod is provided at E, D is the dredge line, and G is the point where there is a zero deflection. So as if it is going to be completely fixed. So G, if you rotate it by 90 degree, it becomes a beam. So you have a beam where the free end is called this point A, and the anchor rod is provided at E. So this is the force, and G, there is no deflection. So this is the beam you can consider, and if this is the kind of loading over the beam, this is the I is the point of inflection. Point of inflection means from sagging it is going to be hogging. So the point where it changes from sagging to hogging or hogging to sagging is called point of inflection. And the bending moment is also going to change accordingly, which is called point of contraflexion. So if this is the kind of loading, and for this loading between A and E, it is going to be a negative moment, hogging, and then it is going to be a positive bending moment, sagging, and at point of contraflexion I, it is going to be again a negative bending moment. So this is the equivalent beam concept. This is positive, this is negative, this is going to be negative, and here this is the force in the anchor rod. So for this kind of loading, any loading, this will be the bending moment diagram. So there is the bending moment diagram for the given beam, and at the point of inflection, if you apply a force P prime, and then it will be hogging on this side if you remove the support. So we have shown this concept of equivalent beam concept, and the pressure distribution is well known to you. Therefore, here, as you have seen between A and E, between A and E, it is going to be a hogging bending moment. And then from here, it becomes a sagging bending moment or a positive bending moment. And then at point of inflection, I, it is going to change like this. So this becomes the bending moment diagram. So for any anchored bulkhead, you need to draw the pressure distribution diagram, and from the equivalent beam concept, you can analyze the whole uh, 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 fixed earth support method. It is called. You can analyze the anchored sheet pile penetrating this. So, what are the steps? How to find out the depth of embedment? Depth of embedment is from the dredge line up to the bottommost point B. This is called the depth of embedment. So, step one is to find out this height H4. H4 is the height. Here you can see that from top up to the water level, it is H1, and then it is H2, and up to this point of up to this point, the pressure is going to be here 0, and then it comes to this side, and then it becomes like this. This height from the dredge line is S3, and up to point of inflection it is H4. So H4 you need to calculate. Now H4, how to calculate this H4? In order to calculate this H4, it is a function of angle of shearing resistance. So for different value of phi, let's say phi equal to 30 degree, 35 degree, and say 40 degree, the value of H4 divided by H1 plus H2 is 0.08. Then 0.03, and this is 0. So this is the value of H4. So depending upon the value of phi, you can find out the value of H4. H1, both H1 and H2 are known to us. So the denominator is known to us, and therefore we can find out this value of H4. That means we can find out up to the point of inflection from the dredge line, the height H4 can be found out. Having found out the value of height H4, now between I and E, we want to find out the span of the beam. Let's say between I and E, the span is L. So between I and E, the span is given as L. So next step will be to find out the span of equivalent beam. So you should find out. So this is between I and E, between this, and that value is L. So you can find out the value of L, which is equal to, between I and E, look to this figure, figure A. Here between I and D, the distance is H4. So it becomes H4 plus it becomes H2. So H2, and from water level up to the anchor rod, that is the point E, it is small h2. So the span can be easily found out because you have already found out the value of H4. H2 is known and small h2 is also known. Therefore, the span is known to you. Having found out this span, you can find out the total load between I and E. What is the total load? So between I and E, find out the third step, total load, say capital W, on a span L as shown in the figure. So how will you find out? That is equal to area of this earth pressure distribution, area of pressure distribution between I and E, between I and E. So having got this area, you can calculate the total load. So total load W on a span L is the area of this pressure distribution diagram. And for any given bulkhead, anchored bulkhead, you know the pressure distribution diagram, and therefore easily you can find out the area. Having got the area, you can uh, mm, find out the total load. So, friend, it is very simple, and then you can find out the maximum bending moment, because the maximum bending moment is going to be between I and this point E, and the maximum bending moment is above the dredge line itself. So we can find out the maximum bending moment. So let's find out the maximum bending moment. Having found out the value of W, the next step is to calculate maximum bending moment, max, you know it, it's very simple. You have already calculated the weight between I and E multiplied by the span length L divided by 8. So that gives you the maximum bending moment. Having found out the maximum bending moment, now you can find out the force P prime at the point of contraflexion I. What is the force here? The force is P prime. This force is P prime. So this force of P prime, you can find it out. So calculate P prime, calculate P prime as shown in this figure A by taking moment about E, by taking moment of area, moment of pressure area about E. So therefore, if you take the moment P prime into L, so here it is P prime, and between I and E, the length is going to be between I and E, it is going to be L. So P prime into L is the moment about E must be equal to moment of area which area? The pressure area. And what is the pressure area? it is going to be A, C, D, I1, I. So A, capital C, capital D, I1, I. So moment of this about E, uh, about E. So you can find out. Therefore, you can find out P prime equal to this divided by L. So moment of the area A, C, D, I1, I, this pressure about the point E divided by L will give you the force P prime. So P prime, it can be easily calculated. Once you do this, you know the maximum bending moment, you know P prime, and therefore you can calculate the depth of embedment. So what is the depth of embedment from the dredge line up to the bottommost point? So let's now calculate the depth of embedment. So the next step will be to calculate D. So calculate the depth of embedment. D as D equal to H4, this distance up to the point of inflection, plus 1.2 into under root 6 times P prime. P prime we have already calculated by taking moment about T of the pressure distribution diagram divided by K prime into gamma prime. So this is the expression for finding out depth of embedment, where K prime equal to coefficient of passive earth pressure minus coefficient of active earth pressure. And gamma prime is the unit weight of the this. So depth of embedment will be H4, this from dredge line up to this point, and then plus 1.2 times under root 6p prime divided by k prime into gamma prime. And p prime already in a step 5 you have found it out. Therefore, from expression 2, you can find out the depth of embedment. Now, how to find out the force in the anchor rod? Let's say the force in the anchor rod is F. So next step is to find the force in the anchor rod. So in fixed earth support method, you are in a position to calculate the depth of embedment, and the last step is to calculate the force in the anchor rod. So force in the anchor rod is shown here as F equal to 1 upon the span, because if you take moment about I, it will be F into L. So F into L equal to 1 upon L divided into moment of area small a, capital C, capital D, I1, I about I. So take the moment about the point of inflection, and already the area is known to you. Take the moment about I. So about I, if you take the moment, this will give you the force in the anchor rod. So friends, very easily fixed earth support method can be applied for analysis of anchor bulkhead or anchor sheet pi, and we can do the complete analysis in a very simple manner. So I hope you have understood it well. Thank you very much.